Welcome to the 5-minute clip on the paper Designing BERT for Convolutional Network, Sparse and Hierarchical Masked Modeling. It is basically about masked modeling. For dealing with masked image, traditional transformer-based method is used. However, at here, they introduce a new CNN-based approach. The masked autoencoder is indeed a method of representation learning. Here, BERT proceed with self-supervised learning with the masked input sentence. Inspired by this method, the masked autoencoder masks the input image, performs position embedding on each patches, and feeds them into the encoder and then reconstruct the image by decoder. The reason for using a transformer is that when an image is masked, it can distinguish between the masked and unmasked part through positional embeddings. This allows for selective feature extraction from the unmasked part. In other words, it is efficient because it can learn features excluding the masked part. However, slide-based convolution processes the masked part with a masked part. However, there is also a problem with BERT-style pre-training. It struggles with learning multi-scale features. As a solution, an extension to using convolution neural networks has been attempted. However, CNN also present a challenge as they are not equipped to handle masked input image properly. Looking at this figure, it is showing the data distribution before after masking. Transformers are capable of preserving the data distribution well after encoding, but CNN leads to the severe data distribution shift. This figure shows well the actual example of convolution at masked image. Here, black area is 1 and white area is 0, masked part. In ordinary convolution, if the filter covers any black unmasked point, the result will be black. This means that in traditional convolution, we could lose information from the masked point. So how can we avoid losing the information from masked pixels during convolution? The solution is not that hard, simply by using sparse convolution. Now we use convolution instead of fixed patches in the transformer, allowing us to learn multi-scale encoded features. Then using a decoder, we reconstruct images from these features.
So how does this sparse convolution work on images? Sparse convolution takes advantage of flattened 3D point clouds to provide a clever implementation in which only unmasked pixels are used for the convolution and thus preserving structures in the image. Taking a good look again at what it means in terms of data distribution, well, it turns out that it preserves most of the original form. In this slide, we can see the effects of a normal convolution on the left side and a sparse convolution on the right. If we consider 3 by 3 convolutions, the set of active non-zero sites grows rapidly. And with the so-called sparse convolution, on the right side, we can see that the set of active sites remains unchanged. Active sites look at their active neighbors green, and non-active sites are red, have no computational overhead. In this slide, we see an overview of the Spark architecture. Since the only major change in this architecture is the form convolutions are applied, backbone networks do not need to be changed. This means that you can still use ResNet and derivations to perform a task. The left side introduces sparse convolutions to overcome the problem with inactive pixels in mask modeling. And between both hierarchical encoding and decoding, it is possible to learn multi-scale features which transformer-based models struggle to represent. During pre-training, the encoder learns multi-scale features, and after pre-training is finished, the decoder part of the network is removed and replaced with a downstream task-specific head. In this paper, they explore pre-training two networks, ResNet and ConvNext, on ImageNet, and evaluating them on different tasks. The pre-training parameters are found in these tables. How does this pre-training strategy compare to other ones? It turns out it improves accuracy and average precision on various tasks. In the top left, we can see what type of unsupervised pre-training strategy they've used previously, and its performance on ImageNet classification. On the bottom right, you can see the results of comparing supervised and unsupervised pre-training in different models. It can be seen that masked image modeling and convolutions create an advantage when compared to traditional transformer-based models. Overall, Spark adapts masked modeling for convolutional net, leading to improved performance in downstream tasks. Given the sparse nature of point clouds and masked images, the authors suggest treating unmasked patches as sparse voxels and using sparse convolution to encode them. Spark utilizes a hierarchical decoder to fully harness the advantages of convolutional nets hierarchy. Spark also creates a flexible framework that can be used by any backbone network. In this slide, we'll see how it works overall.